Okay, so we're going to describe the impact of sample size and population proportion on our sampling distribution. We're going to recognize when the central limit theorem is applicable. And then we're going to perform probability calculations based on the central limit theorem. So the Centers for Disease Control and Prevention, who would have thought in 2004 that that would be like an organization that we'd be looking at like every single day, you know, CDC. I got to know, what's the CDC say today? So they reported that 20.9% of American adults smoked regularly in 2004. So the problem is telling us to treat this as a parameter for the population of American adults. So we're going to go by what they're telling us to do. So observational units and corresponding and the variable corresponding to this parameter. Now, I want to make sure that I'm reading the problem right. The observational units and the variable corresponding to this parameter. So observational units are, Kaylee's not here. Angelica's not here, so we got both of them out of the magic bowl. Let's see who's left. Okay, Isabella, what do you have as the observational units here?
Is it the American adults currently?
I think it's American adults. So observational units, American adults. And what is the variable? Okay, so writing this down just like this has clarified it for me. I was getting a little bit nervous about my own understanding here, but now I understand. So what is the variable here? And is it categorical or quantitative? Mila?
The variable is whether they smoke regularly, and that's categorical.
Yep. So the variable is smoke regularly. And that is a categorical, and I would also say that that is a binary, wouldn't you? You either do smoke regularly or you don't smoke regularly. Everybody okay with that? Okay, great. So what symbol represents the population proportion of 0.209? Isabella again.
Sorry, I'm looking at my notes.
Okay.
Would it be pi?
It would be pi. Pi is the population proportion of 0.209, which is the same thing as 20.9%. But when we're talking proportions, we're going to use decimals between 0 and 1. Okay, so we got that. That's good. I am going to take a random sample of 100 American adults. Okay, I'm just going to go into the population, randomly pick out 100 people, and I'm going to find out whether they smoke regularly or not. Okay, will that proportion of people that smoke regularly be exactly equal to 0.209? Emily?
I think it wouldn't be exact, but I think it'd be very close instead.
I think that's a very good answer. And why do you think it'd be close? I'm not disagreeing with you, but I'm curious as to why do you think it would be close?
Because it's like with statistics and parameters, it's not exact. It's pretty much an average for the most part. So I think that you can still apply that idea that it will be an average to like these calculations as to the sample. So, and we discussed that like the central limit theorem means that like the average of the averages will be very close to the average of each individual sample, but I don't think it would be exact.
And well, could it possibly be exact? Could it possibly be 0.209? Is that possible that that could happen?
I think it is just very unlikely.
Okay, so I understand what you're saying, but actually, what is 0.209 of 100 people?
Would it
So
be
if I go 0.209 times 100, what do I get?
20.9?
Yes, and can I have 0.9th of a person?
No.
So I couldn't even possibly get 0.209 if I wanted to. I could get 21, I could get 20, but I couldn't get 0.209. I couldn't get 20 or 0.09. But I think you're right. Now, and I think a sample size of 100, I mean, yeah, I think it'd probably be around there, but let's kind of find out. Okay. So it's not going to be exactly equal to 0.209. So what does the central limit theorem say about if I did this, if I took 100 people out and I got their proportion, and I took another 100 people out and I got their proportion, and another 100 people, I took them out, and I did this over and over and over and over and over again, what's the distribution of all those proportions going to look like? Crystal, can you help me? And Michaela's not here. Okay. Magic Bowl, you get called a lot when there's very few people. So, okay. Isabella again. What a surprise. I mean, the odds are getting, the size of the Magic Bowl gets smaller and smaller. The probability that you're going to get called on gets higher. Okay, so what does it say about shape, center, and spread?
Will it be unimodal and symmetric?
It will be unimodal and symmetric. All of those different sample proportions that I get will make a nice unimodal and symmetric histogram, and we're going to smooth that out by putting this curve on top of it. And what's it say about the center? What's the center going to be?
The population proportion.
Which is what?
Is it not 20.9?
It is.
Oh, it is. Okay.
0.209. That's what they told us in the problem. See, they said this is the parameter value for the population of American adults, 20.9%, so 0.209. Are you good with that?
Mm-hmm.
Okay, and then let's calculate the spread. So I'm going to take the square root of 0.209 times 1 minus 0.209 divided by n. What's my n? Anybody?
100.
And my n is 100. Great. So let's do that. Let's find out what it is. So I have hang on one second. Okay, that's good. So I go 0.209 times 1 minus 0.209, and I divide that by 100, and then I take the square root of that, and I find out that my standard deviation, let's call it 0.041. Is that okay with everybody? So my standard deviation is equal to 0.041. Well, that's good to know. So let's go, so let's go 0.209 plus 0.041 plus 0.041 plus 0.041. And I'm going to get my different markings on this. So I have 0.250, 0.291, and 0.332. And then let's go 0.209 minus 0.041. minus 0.041 minus 0.041. And on this side, I have 0.168, 0.127, and 0.086. Is everybody okay with that? Okay, now, what do I label the x-axis on this diagram right here? Emily, what do I label the x-axis?
Would it be the proportion of Americans who smoke regularly?
Yes, so we're going to call it proportions of Americans who smoke regularly. And I'm going to put underneath that n equals 100, because I want to be clear that this is based on a sample size of 100, right? Because if I have a larger sample size, it's going to be different numbers. Everybody with me there, right? The larger sample size, the standard deviation is not going to be 0.041. The standard deviation is going to be something smaller. Yes? Okay. All right. So I have my diagram. This is great. Got my diagram here. Oh, we just drew the normal curve. So let's just take it and snip it and see how we like it here. And we'll put it right here. And we'll actually make it a little bit smaller. Even smaller. Okay, that's good. Can everybody see it still pretty well? Yes? Okay. So it says shade in the area where the proportions exceed 0.25. Okay, well, that just happens to fall nicely right on here on my standard deviation. Let's go 1, 2, 3, -1, -2, -3. So that just happens to fit right there on the first standard deviation. So I'm shading in that area right there. What is the z-score at 0.250? Sandra, can you give me the z-score at 0.250? Oh wait, you just sent me a text a minute ago that said she's out for a minute. Not again, there we go. Mila, can you give me the standard deviation at 0.250? I mean the z-score at 0.250.
To find the z-score, would you use the equation? So z equals x minus x bar over the standard deviation.
Okay, so what's my x?
So the x would be 0.25.
Uh-huh.
And then x bar would be 0.209.
And that's divided by?
And the standard deviation, which was
0.041, I think we used, right?
oh yes.
Right? Okay, now everybody watch this carefully, okay? 0.25 minus 0.209. And I'm going to divide that by 0.041, 1, right? Because the z-score is the same thing as the standard deviation, right? That's it. Everybody follow me here, right? So we could even done that without even using the formula because it just happened to fall right there on that line. Everybody okay with that? This is an important point that a lot of people forget, that the standard deviations that we put on our model right here, those just happen to be our integer value z-scores. There's a lot of z-scores between 1 and 2, between 2 and 3 that we have to use a formula to calculate, but these are z-scores also. They just happen to be integer values of z-scores. Okay, so the z-score is 1. So here we go. I reached into the American population. I pulled out 100 people at random, and I want to know what is the probability that that sample that I just pulled out will have 25% or more smokers. I'll say the question again. I reached into the population of Americans. I pulled out 100 people, and I want to know, well, what's the probability that the 100 people that I just pulled out will have 25% smokers or more than 25% smokers? You follow the question that I'm saying here? So I'm going to use my TI calculator here. I'm going to say, okay, I want to know what is the area under the curve right here. Well, I know that this has a z-score. My left z is equal to 1. My right z is equal to infinity. So second distribution, normal CDF, 1, 99. 15.87. So it's 0.1587. So it's about a 15.87% chance that that sample I just pulled out is going to have 25% smokers or greater than 25% smokers. Do you understand what I just did there? Everybody follow what I just did? Yeah. Well, that's pretty interesting. That's really interesting. So let's just we're going to probably stop, but I want to comment here. No, let's do this. Let's do this problem too. I'm going to take a random sample instead of 100 people. My random sample is going to be 400 people. Will the probability, now think about this carefully, will the probability that out of these 400 people, 25% or greater will be smokers, will that be a higher probability or a lower probability? Yeah, I'll bring it back to the diagram here. This is the diagram here. Now, instead of a sample size of 100, I'm taking a sample size of 400. Is the probability that I'm going to have 25% or greater smokers a bigger probability than with a sample size of 100 or a smaller probability? Put your answer in the chat. Put your answer in the chat. Smaller or larger probability? Well, Emily, now I'm going to really penalize you because I say get rid of the question mark. Not only do I say now you put it in writing. Come on, no, I want you to rewrite it with an exclamation point. That's better. Oh, period is okay. All right, that's all right. Yeah, no. Certainly don't commit it in writing. Don't do that. All right. Yeah, it's going to be smaller because my standard deviation is going to be less. So my curve is going to be narrower. A much smaller I don't know what it's. Well, I think it tells us to calculate it. So let's actually do the calculation. Okay. So yeah, sure, we can do this real quick. So I need to calculate my standard deviation, which is going to be 0.209 times 1 minus 0.209 divided by 400. So let's get my calculator back up. So I have 0.209 times 1 minus 0.209, and I'm dividing it by 400. Oh, so this is I got to take the square root of that. I almost forgot to take the square root. That would be bad. So I have a standard deviation, and let's call it 0.020. So my standard deviation is 0.020. So now I have my model, 0.209. Then this is going to be 0.229, 0.249, and 0.269. I'm just going to stop there. So I know that 0.250 is a little bit to this side of 0.249. Everybody see that? Yeah. And I can see if this is 0 standard deviations and this is 1 and this is 2. The last problem, I was like way over here at 1. It's going to be a much smaller number now because I'm like at the second standard deviation. So my z-score is point x 0.250 minus 0.209 divided by my standard deviation now of 0.020. So 0.250 minus 0.209 divided by 0.020. My z-score is 2.05. Z equals 2.05. And so I want to find the probability. I want to find this area here. Second distribution, normal CDF. The z-score I came up with was 0.205, 0.205, comma. No, that's not true. 2.05. Don't do that, Mr. Jenkins. 2. Second distribution, normal CDF, 2.05, comma, 99. Come on, what's the matter with you? Well, this area here now is 0.0201. This is a little bit better than a 2% chance of getting 25% smokers. So we're able to use this now to calculate probabilities. What's the likelihood that something really happens like that? Okay, I took you right up to the bell. I don't like taking you right up to the bell, but I did. So we shall continue on Wednesday. And the stats test, I think I already said, that's due today, right? You already know that. Okay. All right. Thank you, ladies. We'll talk to you later. Have a good afternoon.
Thank you.
Thank you. Question? No. Good. Okay.